New type of prime numbers according to trigonometry. Some years ago I published a video on my other channel where I presented a new way to generate primes. Now I'm back with a new video where I will describe what I call the trigonometric primes. Here's the magical formula. Sine square of pi over 2 times x times p plus x over 2 plus cosine square of pi over 2 times x over 2. If the previous number of the sequence is odd, the cosine function is 0. If the number is even, the sine function is 0. Here, the number is even. The cosine function is square. That ensures the value of the function is either 0 or 1. For previous even numbers, the value of the function is 1. For previous odd values, the value of the function is 0. Here, the number is odd. The sine function is square. That assures the value of the function is either 0 or 1. For previous odd numbers, the value of the function is 1. For previous even values, the value of the function is 0. If the previous number is odd, then according to the sine function equal to 1, the following number, let's suppose we're checking if 13 is prime, will be equal to p plus x over 2 with p equal to 13. If the previous number is even, then according to the cosine function equal to 1, the following number will be equal to x over 2. Here's the odd component, and here's the even component. These are the rules. First number of the sequence is 1. P is equal to the number we want to check. X is equal to the previous number. Let's verify if 11 is a prime number. In order to check if a number is prime, one always starts the sequence with the number 1. So 1 is odd. 11 plus 1 over 2 equals 6. 6 is even. 6 over 2 equals 3. 3 plus 11 over 2 equals 7. 7 plus 11 over 2 equals 9. 9 plus 11 over 2 equals 10. 10 over 2 equals 5. 5 plus 11 over 2 equals 8. 8 over 2, 4. 4 over 2, 2. 2 over 2, 1. The cycle ends in 1, and then repeats itself again until reaching 1 again. There are 11 items between each cycle, when one starts in 1 and ends in 1. The number we want to check is 11. And the number of items between ones is 11, so 11 is a prime number. Here's the list from 3 to 31 with all odd numbers. In white we have the prime numbers. Here in gray we have the primes which are not trigonometric. The columns begin with 1 and end with 1, but they do not have the same items as the number we want to check. In order to verify if they are primes, one must extend the column. That means the number 1 will appear more than twice when one wants the number of items to be equal to the number itself. Now let's check a number which is not a prime. When the number 1 appears twice, the number of items is different from the number itself. And here's the list from 33 to 61. As you can see, 37, 53, 59, and 61 are trigonometric primes. And here is the list of the first trigonometric primes. We have 3, 5, 11, 13, 19, 29, 37, 53, 59, and 61, and so on. But there is a problem with some numbers. They are called pseudoprimes of base 2. Though they are not trigonometric, they will appear as primes, using this method. The number 1 appears more than twice, but it appears at the end when the number of items is equal to the number itself. For example, 341 and 561. Nevertheless, they won't appear that often. And for this matter, that is not a problem, since we're only searching for trigonometric primes. So, the conclusion is that there are these new types of primes one can calculate using this equation. I decided to call them trigonometric primes. Their behavior is different from non-trigonometric primes. Thus, it should be treated as a new special category of primes.